what is our universe made of? Whenever we talk about the universe, the first things that come to people's minds are images of galaxies, stars, many different colors, all amidst the darkness. But only 5% of the universe is made up of visible matter, which is the matter you think of when you see galaxies and stars. Most of our universe is made up of dark matter and dark energy, which are precisely things that we don't exactly know what they are. But in our daily lives, it is this 5% of visible matter, which in physics we call baryonic matter, that affects our lives. Everything you do, from eating to watching a series on streaming or getting out of bed, involves interactions with visible matter. Our body, and basically everything we see around us, is made up of a very complex puzzle of atoms and particles, which we essentially know as matter. And this puzzle of these components is extremely detailed and explained by the Standard Model of physics. The Standard Model describes the fundamental particles that give rise to the atoms that make up everything we see and touch in our daily lives. It is considered the most successful model in physics because all of its predictions have been confirmed sooner or later, such as the Higgs boson. But more than just describing particles, the Standard Model also describes some of the possible interactions these particles can have with each other. Getting up or opening the streaming app on your phone involves a series of interactions between particles, almost like a quantum game of telephone. There are 4 possible interactions that we see happening in the universe. The Standard Model explains 3 of them, and the last one is explained by general relativity. And these are known as the 4 fundamental forces of the universe, and in this video we will get to know each one of them.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
The 4 fundamental forces or interactions are the gravitational force, the electromagnetic force, the strong force, and the weak force. 2 of them are quite famous, and I'm sure you must have studied or heard about them at some point in your life. And the reason is not just that they are more famous or well known, but that both the gravitational force and the electromagnetic force are the only forces that act on large scales, from us humans to galaxies. So let's start with gravitational force. The understanding of gravity began when Isaac Newton published his law of universal gravitation, which we can summarize by the famous equation F equals gm1 m2 over e2. Basically, the law states that 2 bodies with masses m1 and m2 will have an interaction that is inversely proportional to the square of the distance between them. The farther apart these bodies are, the weaker the interaction between them. The first step was taken to understand this fundamental force of nature. Another step was taken centuries later by physicist Albert Einstein studying Newton's equations. Einstein was troubled by some problems with Newton's equations and introduced the theory of general relativity as a solution. For general relativity, gravity is the distortion of space-time caused by the mass or energy of something. In other words, the Earth is gravitationally bound to the Sun because the Sun distorts space-time with its mass, and we are bound to the surface of the Earth because the Earth distorts space-time with its mass. Einstein's theory has been so successful that, even a century after its publication, we have not found any flaws in the scales at which it operates. And it was thanks to Einstein that we came to understand gravity as a part of the geometry of the universe itself and not just as a force vector between 2 masses, which was Newton's view. But this doesn't mean we need to leave Newton's universal gravitation behind. It is perfectly acceptable to continue using Newton's equations for gravity, or even the term force, when referring to it at certain scales. The gravitational interaction, whether we are using Newton's or Einstein's approach, has some interesting characteristics. The first of these is that gravity is the weakest interaction among all 4 fundamental interactions in the universe. It is up to approximately thousands of billions of times weaker than the strong force, for example. And that wasn't a play on words, it's a fact. And the second interesting trait is that it's not always the strongest that stands out the most. Because gravity, as the weakest force, dominates the largest scales of the universe, like in the inevitable collision between the Andromeda and Milky Way galaxies, which is our galaxy. And not only that, since the gravitational interaction is valid for very large distances, any body with mass anywhere in the universe is interacting with all other bodies with mass. So yes, the supermassive black hole M87 star, which is 55 million light-years away, is gravitationally interacting with me. But this interaction is so small that we can simply ignore it, as it will never make a difference in our lives. But remember, even though it is very small, it is not zero. And this shows how powerful and important the gravitational interaction is. The gravitational interaction also brings some problems within physics and questions that, as I mentioned before, have remained open for centuries. But to explain this, we first have to move on to the second force on our list. The second force or interaction is the electromagnetic force, which is responsible for everything from our vision to the charger you use to charge your phone or the computer you're watching this video on. And not only that, the electromagnetic force is also responsible for keeping two components of atoms, electrons and protons, interacting. Thus the possibility of atoms forming and chemical reactions occurring. And one reason for mentioning this force now is that besides being the second one we know the most about, it is very similar to the gravitational force in mathematical form. F equals K times Q1 Q2 over R2. This equation is also called Coulomb's law, because it was first published by the physicist Charles-Augustin de Coulomb at the end of the 18th century. And if you look at the equation, you'll notice that it has properties very similar to those of the universal law of gravitation. The first of these is that it also decreases with the square of the distance between the charges. So it has a range of action similar to gravity. And this is true. Two charged particles will interact despite the distance, whether they are in the same atom or in another galaxy. And the interaction becomes weaker as the distance increases until it reaches extremely low values that we can ignore, but it never reaches zero. But it is this fact that can start to answer some of our questions. Unlike gravity, the electromagnetic interaction is already well explained by the Standard Model. We know the particles that interact closely with each other and also the particles that mediate the process. Wait a sec. Particles that mediate the process? Isn't it just the proton and the electron interacting? So besides the particles that participate, which are the protons and electrons, we also have the so-called messenger particles, or, in a more elegant way, the gauge bosons. All three fundamental interactions in the Standard Model have their associated elementary gauge bosons. An electromagnetic interaction involves photons, virtual photons. Their existence is temporary and they act only for interaction. One way to imagine how these virtual photons act is as follows. Imagine that you and I are sitting across from each other in those wheelchairs, like the ones in an office. I am standing still with a ball in my hand. You are standing still with a ball in your hand. Then I throw mine to you and you throw yours to me. We will both transfer momentum to each other, causing the wheelchairs to move apart. That's basically what virtual photons do. They are responsible for the interaction between the two charged particles. Repel with equal charges or attract with opposite charges. Still with the idea of the office chair explaining the attraction, do the same experiment, throwing a boomerang so it makes a half circle and comes back to us. Speaking in physical terms, virtual photons are essentially the way charged particles find to return to the lowest possible energy state. It's as if, when two particles with equal charges are close to each other, they are in a higher energy state and need to move apart to return to a lower energy state. In the case of two particles with different charges, they need to come closer to reach the lowest energy state. And the ones mediating this interaction are the virtual photons. There is something else curious about them. Photons have no mass, and mass indeed plays an interesting role when we consider the distance these photons can travel. Both the existence of virtual photons and the lifespan they can have are described by Heisenberg's uncertainty principle in terms of energy and time. And when we analyze the distance through d equals c times delta t, we arrive at the following formula. If we consider the mass to be essentially zero or set a limit of m approaching zero, the distance begins to approach infinity. In other words, the range of the electromagnetic interaction mediated by virtual photons is infinite, just as we conclude from Coulomb's law. And if you have been waiting to explain what the problem with gravity is that I mentioned earlier, here we can start to understand. We have already concluded that the law of universal gravitation and Coulomb's law are very similar and have a range of action that is practically infinite. So, the justification for this must be similar. The gauge boson responsible for gravity must have a range with the distance given by this equation, tending to infinity. For this, it is necessary that the mass of this boson be zero, exactly like that of the photon. This provides a way to explain gravity and the characteristics of the gauge boson responsible for it. And this boson even has a name, graviton. The problem is that we have never observed a graviton, so its existence is still uncertain. And furthermore, the theory of quantum gravity is not yet well established enough to start answering these questions and to include gravitational interaction in the Standard Model through gravitons or some other means. But the Standard Model explains well the electromagnetic force and two other forces called the strong force and the weak force. I just mentioned that particles with the same electric charge repel each other, and the closer they are, the stronger this interaction is. If you look at the nucleus of an atom, you will notice that it is basically a bundle of protons and neutrons together in a small space. And how exactly do these protons and neutrons stay together if their charge is the same? Shouldn't they just repel each other violently? And the answer to that is the strong force or strong interaction. The strong interaction is responsible not only for keeping protons and neutrons together, but also for holding the components of these particles together. Each proton and neutron is composed of 3 quarks. In the case of the proton specifically, 2 up quarks and 1 down quark. And in the case of the neutron, namely 2 down quarks and 1 up quark. Additionally, each quark can have a charge called color charge, which is not the same as electric charge. The color charge in fact comes in 3 types: blue, red, and green. And the mixture of the 3 is called white, and there is something similar in combining positive and negative charges to neutralize. But one important thing is that when we talk about color, we are not saying that these fundamental particles actually have colors. It's just an analogy to illustrate that by combining the 3 colors, you get a neutron. It's the fault of physicists who lacked creativity in the 50s. Every proton and neutron must have all 3 colors. That is, in fact, each of the 3 quarks actually has one of these colors, and it indeed extends even further. Quarks can change color. In fact, they change color almost constantly all the time. The gauge bosons responsible for this are known as particles called gluons. Gluons also have color charges, and they only interact with other things that also have color charges. That is, quarks and other gluons. They function more or less like elastic bands. If you've ever felt a rubber band pulled and released, you know that the more it stretches, the stronger it snaps back. Gluons create a kind of rubber band in quark interactions and color changes. If you try to pull one of these quarks, this elastic will pull back with increasing force until it reaches a point where the quark can no longer move away. And this interaction is called the strong force. It is different from other forces because the farther apart the quark is, the stronger it becomes. However, there comes a point where the force is so very strong that the quark hardly ever leaves the particle, and that's why protons are so stable. For this reason, and because gluons have charges, the strong force operates on such a very small scale that it is not even comparable to gravity, even though it has 0 mass. Precisely because of what I mentioned earlier, gluons, having 0 mass, could reach infinite distances like photons. However, unlike photons, gluons possess this charge and interact with each other, limiting their range. But if you manage to put an absurd amount of energy into these quarks, like the energy present in the core of the sun, they can even escape from their particles. And the energy required to break the elastic band created by the gluons is so enormous that when a quark leaves, a quark and an antiquark are formed in its place. The quark returns to its place within the proton or neutron, and the antiquark forms a component called a meson or pion together with the original quark. And these mesons go from one neutron or proton to another and act as gauge bosons in a way very similar to gluons. They are responsible for holding the atomic nucleus together and for having mass. And when placed in the equation, you will find that they have an extremely small range, which is practically the size of a proton. And it is thanks to these mesons and gluons that atoms can remain stable and that we indeed exist. And finally, we have the last interaction, the weak force or weak interaction. The weak interaction is also present in the lives of protons and neutrons. But how can anything even compete with a force as strong as the strong force? Some even find it strange to call the weak interaction a force. It works more like a kind of trick or power that protons and neutrons possess. A neutron can become a proton, or a proton can become a neutron. And think about how incredible that is. One particle can simply become another particle. And this exists because an up quark can become a down quark or vice versa, and well, protons and neutrons are made of quarks. You take a neutron that has 2 down quarks and 1 up quark and change one of the down quarks into an up quark and you have a proton. And the ones responsible for this change are the W bosons, which can have positive or negative charges. When a quark in a neutron switches from down to up, it emits a W boson with negative charge. So, the particle that was neutral before, the neutron, is now a positive particle because it actually lost a negative charge. The W- boson in turn is massive and unstable. Then, 15 minutes later, it decays into an electron and an antineutrino. Using our equation to get the range of this interaction, since the W boson has mass, its range is only 0.1% of the size of a proton. In other words, it is very necessary for you to be extremely close for this interaction to begin in the first place, making it rare but still important. And that's because the weak force and the electromagnetic force have a very important relationship within physics, which is the electroweak interaction, basically the first unification discovered. But that will be for a future video, as well as the origin of these fundamental forces and how they are associated with the grand unification of physics. And, to conclude, recently, the Fermilab collaboration running the particle accelerator in the United States announced the possible discovery of a new force, the fifth force. That's because they repeated an experiment this year and got the same result as before. Basically, muons, which are particles similar to electrons, were accelerated, and when they analyzed the frequency at which these muons oscillated, they noticed that it was as if there was another force pulling them. The experiment became known as muon G2. The physicists in the collaboration argued in a paper that there might be something new here, possibly a new particle or a new force. If confirmed, this could be the fifth fundamental force of nature. The Fermilab collaboration stated that they will redo the experiment in 2 years, once they have more data and more sensitive data. So, who knows? In 2 years we might have an answer. So, if everything goes well, in 2 years I will remake this video and the title will be updated to The 5 Forces of Nature Explained. And besides that, I know many people must be curious about dark energy, as it is basically the antagonist of gravity. We already know that, on much larger scales, gravity starts to lose to what we now know as dark energy. While gravity attracts, we see that very distant galaxies are moving away at an accelerated rate, almost as if there is a force pushing them and overcoming gravity. Some scientists believe that yes, dark energy is indeed another force of nature, but we still know very little about it. So, it is still too early to say whether we are indeed dealing with a new force or something different, which is why we call it dark energy. And while we're on the subject of mysteries, dark matter, not to be confused with dark energy, only interacts through gravitational interaction, leaving the other interactions still a big question mark. And I could make another video just with all the things that are still not explained using the 4 fundamental interactions. Let me know if you would like to see that in the channel. Thank you very much and see you next time.